In this video, we're going to talk about angles inside the circle and also segment lengths of intersecting chords. We're also going to talk about angles on the circle and outside the circle, and also the lengths of outside segments. So there's a lot going on in this video about circles. First, we're going to start with the inside segments, so intersecting chords, and we're going to start with the angles that they form, the vertical angles that they form. So angles inside the circle that are formed by intersecting chords are half the sum of their intercepted arcs. So if you take a look at the diagram that's here, we have intersecting chords JL and MK, and they create vertical angles. And I'm just going to outline one set of the vertical angles here. And in order to find these vertical angles, I would take half the sum of their intercepted arcs. So let's say that these two arcs, which are the intercepted arcs for those two vertical angles, let's say that they were 30 and 60 degrees, and I'm just making this up. Then in order to find one of the vertical angles, and I'll put that here, in order to find the vertical angle, I would do half the sum, that means plus, the intercepted arc. So half of 30 plus 60. And that would give me my vertical angles. So in this case, with these numbers here, we would have 45 degrees for the vertical angles, which are always congruent. Let's do some practice with this theorem. In the diagram below, chords AB and CD intersect at E. If the measure of angle AEC is 4x, the measure of arc AC is 120 degrees, and the measure of arc DB is 2x, what's the value of x? So here we have information about this pair of vertical angles created by the intersecting chords. And for those vertical angles, the intercepted arcs are this one and this one. Those are the ones that those chords are touching. So in order to find the angle, the vertical angle, I'm going to write that here, the vertical angle formed by the intersecting chords, in order to find the inside the circle angle, the vertical angle, what we need to do is take half the sum of the two intercepted arcs. So the vertical angle is 4x, and that's equal to half 120 plus 2x. And from here, we can solve the equation. To get rid of the 1/2 on the right side, the easiest way is to multiply by 2, the reciprocal, because 2 and 1/2 cancel out, and you're just left with 120. Oops, sorry, I wrote that really badly. And you're just left with 120 plus 2x on the right side. Whatever you do to the right, you have to do to the left of your equation. And 4x times 2 is simply just 8x. I'm going to subtract 2x from both sides. And then I'm going to divide by 6. And I have that x is equal to 20. For the next example, you should pause the video. You should try it yourself. And then you should unpause the video in order to check your work. The accompanying diagram shows a child's spin toy that is constructed from two chords intersecting in a circle. So once again, we have intersecting chords. The curved edge of the larger shaded section is 1/4 of the circumference of the circle. So the whole way around the circle is 360 degrees. And if I take 1/4 of that, that means to divide it by 4. Let me figure out what that section is going to be. So 360 divided by 4 is 90. So this portion of the arc is 90 degrees. And the curved edge of the smaller shaded section is 1/5 the circumference of the circle. So let me do 360 divided by 5. And that gives me 72 degrees. What is the measurement of angle x? So the angle inside the circle, the vertical angle, formed by the intersecting chord, which are these two that we're looking at, is equal to half the sum of the intercepted arcs. So the vertical angle is x, what we're looking for, and that's equal to half of 72 plus 90. 72 plus 90 is 162, and then half of that is 81 degrees. So the vertical angles are 81 degrees. So x is 81 degrees. Here is our next theorem that we're going to talk about in this video. We just talked about the angle and arc measurements that were formed by intersecting chords. Now we're going to talk about the segment lengths of intersecting chords. So once again, we have a picture of two chords, AC and BD, that intersect in the circle. And when they intersect, we have a theorem that says the part of this chord times its other part is equal to the part of this chord times its other part. So for example, if this was 4 and this was 2, and this was 6 and this was 3 and this was 6, not drawn to scale, the setup of our equation here, let me make something x. Let's make this x. The setup of our equation here would be 4 times 2, so part times part, equals 3 times x. That doesn't work out nicely because I just made up those numbers. But once again, you can also think of this formula as part times part of one chord equals to part times part of the other chord. Let's do some questions practicing using this theorem. In the diagram below of circle O, chords JT and ER intersect at point M. If EM is 8 and RM is 15, the lengths of JM and TM could be what? This is one of those examples where we do need to try out each of the answer choices. So answer choice 1 says 12 and 9.5. Let's try it out and see if it works. Let's do part times part. So 15 times 8 equals to part times part. And let's see if it checks out and it works out to be something equivalent on both sides. 15 times 8 is 120. 9.5 times 12 is 114. So that doesn't check out to be 120. So I'm going to erase. I'm going to erase over here so we can try out the next answer choice. And I'm going to erase what we plugged in so we can try the next one. Let's try 14 and 8.5. So part times part equals part times part equals 14 times 8.5. Let's see if that is equal to 120. 14 times 8.5, that's 119. So that doesn't work. That one's a little bit off. Let's hope the next one is closer. Let me reset so we can try out the next answer choice. 16 and 7.5. Let's see if it's equal to 120. 16 times 7.5, and that is 120. So we are good to go. The correct answer is answer choice number 3. For the next example, please try to pause the video to see if you can answer the question yourself for the next 2 examples that we're going to do, and then unpause to see if you got the correct answer or if there was a part that you got stuck on to see how to complete it. Here we have chords AB and CD intersecting at E. If the length of AE is 3, the length of EB is 4, the length of CE is X, and the length of ED is X minus 4, what is the value of X? So we're talking about segment lengths here, not arcs and angles. So we're going to use our theorem that we used before. Part times part equals part times part. So let's start with one chord. Let's start with AB. So here we have one part and then the other part. So that's 3 times 4. Okay, and now let's do the other part. We have X minus 4 and we have x. So when you're solving, the left-hand side's pretty simple. That's 12, pretty straightforward there. But the right-hand side, remember to distribute the x to both of the other terms. So we have x squared minus 4x. And this is bringing back some Algebra 1 because notice how we have an x squared and this is not going to cancel out. There's no other term with an x squared. So we're going to end up with a quadratic and we're going to have to solve by factoring. So to factor, you do need to make your equation equal to 0. So I'm just going to subtract 12 on both sides. And we do have a trinomial. So just bringing back some Algebra 1 memories, we usually make an A times CB chart. Some of you might have learned this with the box, but it's the same thing this way. And our A is 1. Our C is negative 12. So 1 times negative 12 is negative 12. And our B coefficient is negative 4. And what we're looking for is two numbers that multiply to give us negative 12 and add up to give us negative 4. So I'm going to think of factors of negative 12. The first ones that come to my mind are 4 and negative 3. But if I add those don't make negative 4. Those make positive 1. So that's not what I'm looking for. If I switch the signs, they would still multiply the negative 12. But this time they would add to negative 1, which isn't what I need. It's not what I'm looking for. So I need some different factors between 4 and 3. I'm also thinking of 6 and 2. So if I do negative 6 and positive 2, they multiply the negative 12. And they do add to negative 4. So these are the two factors I'm looking for. So what I'm going to do here is I'm going to keep the first term. We're going to use the factors to rewrite the middle term. So instead of the negative 4x, negative 6x, and positive 2x, the two factors that we found. And notice how those add up to give us negative 4x. So we just replaced the middle term with our factors that we found. And then the last term, minus 12. And then we can factor by grouping. You can group the first and second terms, the third and fourth terms, and then we can look for something in common. In the first set of parentheses, we have an x in common. If I take out the x, I'm left with x minus 6. In the second set of parentheses, we have a 2 that can be pulled out of both, a positive 2. And if I pull it out, I'm left with x minus 6. So our two factors are one is what's outside the parentheses. So the x and the positive 2 are outside the parentheses. And the other factor is what's inside the parentheses, x minus 6. So we have two equations, x plus 2 equals 0, and x minus 6 equals 0. And if you solve, x is negative 2, and x is 6. In geometry, we reject the negative solution because here we're talking about segment lengths of a circle, and it wouldn't make sense for it to be negative because then we wouldn't be able to see it. It wouldn't actually exist. So our x value here is 6. So that's what we're looking for. Pause the video and try out the next one. Make sure to draw a diagram. A toy truck is located within a circular play area. Alex and Dominic are sitting on opposite endpoints of a cord that contains the truck. And it doesn't matter how you draw your cord. It doesn't give us enough information. And it just says the truck is somewhere along this cord. It doesn't say where. Alex is 4 feet from the truck. And Dominic is 3 feet from the truck. Once again, not drawn to scale. Doesn't matter if my drawing doesn't look right. It's okay. Mira and Tamara are sitting on opposite endpoints of another cord containing the truck. So maybe Mira is here, and maybe I'll use TM for Tamara. And their cord is also containing the truck. And look at that. We have intersecting cords. Mira is 8 feet from the truck. How many feet is Tamara from the truck? Since we're talking about segment lengths of intersecting chords, we can do part times part equals part times part. So let's do chord AD first. One part is 4 and the other part is 3. And then let's do the other chord next. we have that one part is 8 and the other part is x. And it's not going to work out nicely because the question does say to round to the nearest tenth. So 12 divided by 8, x is 1.5. So Tamara is 1.5 feet away from the toy truck. Our next circles theorem that we're going to see in this video is about angles on the circle. So angles formed by a chord and a tangent to the circle. Notice here we have chord AB and we have tangent CD. It's a tangent because it only hits the circle at one point B. And when you have an angle on the circle, and by on the circle, I mean that the vertex is on the circle. So notice how the vertex point of this angle is on the circle, or we can look at this angle whose vertex point is on the circle. It works the same way. And an angle on the circle works the same way as an inscribed angle. It's half of its intercepted arc. So for this angle that I have outlined in pink, the arc that it's touching is this arc. So it would measure half of the arc. So let's say the arc was 100. This angle over here would be 50, same as an inscribed angle. Let's check out some examples. In the accompanying diagram, BD is tangent to circle O at B, BC is a chord, and BOA is a diameter. If the ratio of the measurement of AC, arc AC, to arc CB is 1 to 4, find the measurement of angle DBC. And if I just outline angle DBC, notice how the vertex point is on the circle. So it's going to be half of its intercepted arc. And its intercepted arc is CB. So if I can find CB, then I could take half of it and I can find the angle that we're looking for. The ratio of AC to CB is 1 to 4. So this is the 1 part of the ratio. And this is the 4 part of the ratio. And since segment AB is a diameter, it splits the circle in half into a semicircle. So if I put the two pieces, the 1x and the 4x together, I should get half of a circle, a semicircle, which is 180 degrees. So here I have 5x is equal to 180. And if I solve that by dividing 180 by 5, I get x is equal to 36. So this arc over here is 36 degrees. And if I multiply it by 4, I get arc CB, which is 144. And then if I take half of that, I get the angle that we're looking for, the angle on the circle, which is 72 degrees. For the next one, please try to pause the video and try it yourself. In the accompanying diagram, CD is tangent to circle O at point B. AO and BO are radii, so that means that they're going to have the same measurement. I'm going to mark them as congruent because all radii of the same circle are congruent. And chord AB is drawn. If angle AOB is 108 degrees, find the measurement of angle ABD. So we're looking for this angle here, whose vertex is on the circle. So an angle on the circle is half of its intercepted arc, and it intercepts this arc over here. So if I can find that arc, it's half of that. And luckily I can find that arc because we have this angle over here, angle AOB, which is a central angle. And central angles are equal to their intercepted arcs. And angle AOB also intercepts arc AB. So if the central angle is 108, so will the intercepted arc be 108. And then all I have to do is take half of that, and that would be 54. So 54 degrees is the measurement of angle ABD that I'm looking for. In the circle below, AD, AC, BC, and DC are chords. EDF, line EDF is tangent to the circle at point D. And AD is parallel to BC. I'm going to mark that in the diagram. And I'm just going to mark when we have parallel chords, they intercept congruent arcs. So the arcs between them are congruent. Just in case we need that, I'm going to put that in there. Which statement is always true? Let's check them out one by one and see if we can find one that has to be true. 1. Angle ADE, so this angle on the circle, is congruent to angle CAD, this angle over here. I don't think we have any way of knowing that those angles are congruent to each other because that angle CAD, is an inscribed angle, but it doesn't intercept the same arc as the angle on the circle. Because it does work the same way as inscribed angles, where both inscribed angles and angle on the circle are half of their arc, but then they would have to intercept the same arc or congruent arcs to be the same measurement. And angle ADE intercepts arc AD, while angle CAD intercepts arc CD, and arc AD and arc CD are not necessarily congruent to each other. So I'm going to rule out that answer choice. And let's try the next one. Angle CDF, and that is an angle on the circle, and it intercepts arc CD, is congruent to angle ACB. Angle ACB is an inscribed angle, and it is also, just like angle CDF, half of its intercepted arc. And the intercepted arc is AB, so that would be true, because these arcs are both congruent. So if they're both 100, then that's 50, and that's 50, because inscribed angles are half their arc, and angles on the circle are half their intercepted arc. So answer choice 2 is the one that must be true. Finally, our last theorem for this video, we're going to talk about, oh, actually, this is not. This is our second to last theorem for this video. We have a lot of theorems in this video. Angles outside the circle. So angles outside the circle are half the difference of their intercepted arc. So just like angles inside the circle, those vertical angles formed by intersecting chords were half the sum of their intercepted arcs, angles outside the circle are half the difference of their intercepted arcs. And you want to make sure that you do the big arc minus the small arc so that you don't end up with a negative arc, because that wouldn't make sense. So for example, in this picture, let's say we wanted to find angle C, which is an angle outside the circle. It's an angle formed by a tangent and a secant. The segment here is tangent to the circle, and the segment here, or line or ray, whatever you want to call it, is secant to the circle. Doesn't matter. It's the same thing. We would take half of big intercepted arc minus little intercepted arc, the arcs inside the rays of the angle. And then we would have our outside angle measurement. So half the difference of the intercepted arcs, a big arc minus small arc. Let's try an example so we can see how this works. So here we have secant PLKE and tangent PZ drawn from external point P. If arc LZ is 56 degrees, find and state the degree measure of angle P, which is an outside angle. So I'm just going to highlight the rays of the angle so we can see the intercepted arcs. So I see arc LZ is one of the intercepted arcs for the angle, as is. It's also touching these two endpoints, as is this arc over here. What I need to do is I can't have two unknowns in my setup, so I need what arc EZ is. Luckily, EL is a diameter because it passes through point K, which is the center of the circle. So together, arc EZ and arc LZ need to make 180 degrees. So if I do 180 minus 56 degrees, then I get 124 degrees. And now I can set up. So the outside angle is half the difference of big arc and small arc. So half of big arc minus small arc. So angle P is our outside angle, and it's equal to half of 124 minus 56. And if I put that into my calculator, 124 minus 56 is 68. And then if I half that, I get 34 degrees. So that is a 34 degree angle, angle P. Try the next one yourself and unpause the video if you do get stuck or if you want to check your answer. Here, once again, we have a tangent and a secant making an outside angle, angle LMK, which is the one that we want to find the measurement of. So we need to take half the difference of big arc minus little arc. The two intercepted arcs are this one and this one, but we need to figure out what the measurements of those arcs are. We're told that the ratio of ln to nk to kl to the arcs is 3 to 4 to the 5. We can represent ratios with expressions. Arc ln is the 3 part of the ratio, so that's 3x. Arc nk is the 4 part of the ratio, so that's 4x. And arc kl is the 5 part of the ratio, so that's 5x. And if I put the 3x, the 4x, and the 5x together, I get the full circle, which is 360 degrees. So I have 12x is equal to 360. So to find my x value, all I need to do is divide by 12. And I got that x is equal to 30. Now I'm going to plug in. 30 times 3 is 90, so this is a 90-degree arc. 30 times 5 is 150. So this is a 150-degree arc. And those are the only two arcs I actually need here. So the angle, the outside angle, so angle LMK, is equal to half the difference of the intercepted arcs. So the big arc, 150, minus the small arc, which is 90. And if I put this into my calculator, 150 minus 90 is 60. And then if I take half of that, I get 30 degrees. So the measurement of the outside angle is 30 degrees. Two more examples for this theorem. In the diagram below of circle O, we have two secants. And this is going to work the same way. When you're dealing with secants, just like with a secant and the tangent, since it makes an outside angle, it's the same thing. The outside angle equals to half of big intercepted arc minus little intercepted arc. The only difference is in this question, they give us the outside angle, it's 44 degrees. They also give us the big intercepted arc. And what we need to do is find the little intercepted arc. So our solving is going to be a bit different. So the outside angle, which is 44 degrees, is equal to half the big arc minus the little arc, which is what we're trying to find. To get rid of the 1/2, the best way is to multiply both sides by 2, and that cancels out the 1/2. So we have 88 is equal to 136 minus x. If I subtract 136 from both sides, I get negative 48 equals to negative x. And then if I divide both sides by -1, I have x is equal to 48. And x does represent the arc that we're finding. So the arc that we're finding is 48 degrees. And finally, here we have two tangents to the circle. And we're told that major arc BC, so from here to here, is 220 degrees. We need to find the outside angle A. And even when there's two tangents to the circle, it works the same way. Big intercepted arc minus little intercepted arc. So we already have big intercepted arc. We just need to find little intercepted arc. But if we know that the whole circle totals to 360, if we do 360 minus 220, that gives us little intercepted arc of 140. So the outside angle is equal to half big intercepted arc minus little intercepted arc. And that gives me 40 degrees. We have one more theorem left for this video, and I know this video is getting a little bit on the long side, but we have one more left, and that is the segment lengths of outside segments. So we talked about finding angles formed by secants and tangents and arcs formed by secants and tangents, but now we're going to talk about finding the lengths of segments formed by secants and tangents. We're not going to do two tangents because we did that in the previous video that I made. two tangents to the circle from the same outside point are just congruent to each other. So the examples here will be with two secants or a secant and a tangent and finding the lengths. And we have a really nice theorem for that. And I like to write it a little bit differently than what's here. So I like to write it as whole times outside of one outside segment equals whole times outside of the other outside segment. So let's start with secant PR. So we would take the whole, which is PR, times the outside part, which is QR, and that would be equal to the whole other secant, TR, times the outside part, SR. And that's the whole theorem. Whole times outside equals whole times outside. Let's practice using it. In the accompanying diagram, PA is tangent to circle O at point A. Secant PBC is drawn. PB is 4. And BC is 12. Find PA. So we're going to use whole times outside equals to whole times outside because we have outside segments. We have a secant and a tangent. Let's start with the secant. The whole secant is the 12 part plus the 4 part, which is 16. The outside part is the part that's outside the circle, which would be PB, which is 4. Now let's move on to the tangent. The whole tangent is represented as x. And since the whole tangent is outside the circle, the whole and the outside part are the same thing. So the outside part is also x, because that's completely outside the circle. So we have 16 times 4, which is 64, is equal to x squared. And then if we square root both sides, we have x is equal to 8. And the x value does represent PA, which is what you're looking for. So that is our answer here. We're going to do one more example for this video. I recommend that you pause the video, you try that yourself, and then you unpause to see if you got it. Here we have two secants, but it's going to work the same way. PR is 24, so we're talking about the lengths here. We're given lengths, not arc and angle measurements. We're given lengths. PQ is 6. PS is 8. And we need to find PT. So I'm going to write down our theorem over here. Whole times outside equals to whole times outside. And let's start with secant RP first. So the whole secant is 24. And the outside piece is 6. And then on the other secant, the whole secant is represented as x. PT is the whole secant. It's represented as x. It's what we're looking for. And the outside part is 8. Oops. So here we have 24 times 6, which is 144, is equal to 8x. And I have x is equal to 18. And that's it for this video.